Thank you. I'm Thijs. I'll be presenting today Spectre in the real world, leaking your private data from the cloud with CPU vulnerabilities. And what we're going to do is we're going to leak data from other tenants at real cloud providers. So almost 8 years ago, it's January 3rd, it's a couple of days after New Year. 34th Congress just ended, and everybody is very excited to start this new year. Everything is great until these two come along. These two are major vulnerabilities that were publicly disclosed on January 3rd. And Spectre and Meltdown, they showed us that the security boundaries that our CPU provides, they are not as watertight as previously thought. And that's because these Spectre and Meltdown, they abuse bugs in the CPU. That's the hardware itself, and they will do that to leak secret data. And after Spectre and Meltdown, it's now 8 years later. Every couple of months, a new vulnerability has shown up, each with a cool logo, with a cool name. And thanks to very hard work from industry and academia and developers across the world, most of these CPU bugs have mostly been fixed, have been mitigated. And on a technical level, I think like all these vulnerabilities are very cool, super impressive. However, every time I read a headline like, oh, new CPU vulnerability has been discovered, I do wonder two things. The first thing is, are CPU attacks actually possible outside of this curated lab environment? We've learned a lot since 2018, and we've mitigated most of the issues, but the real world, real systems, they are messy, they vary a lot, they have defense-in-depth mechanisms. So the question is, are the CPU attacks still effective, still possible on actual production systems, even when defense-in-depth measurements are in place? And the second question is, from an attacker's perspective, what are realistic and practical use cases for CPU attacks? Because it is kind of a strange thing, because to abuse a CPU vulnerability, you are very likely going to need some form of code execution. And if an attacker already has code execution, then you probably have other things to worry about first. So the question is, like, in what scenario does it actually make sense for an attacker to use these CPU bugs? And it turns out there's actually a very big scenario where it does make sense, and that is the cloud. So yeah, what is the cloud? It is sort of a complicated question depending on who you ask. But for the purposes of this talk, we will consider the cloud to be a collection of physical machines provided by a cloud provider, and you as an individual or a company can rent a virtual machine. And of course, you're very likely not the only person to rent this virtual machine, so there are a bunch of other customers there as well, running their workloads in these virtual machines. And the cloud provider does not want one customer from reading the data of another customer. So these virtual machines are isolated from each other. And we're going to look at this isolation between these virtual machines, and we're going to see whether they hold up if CPU vulnerabilities are taken into account. So what's our threat model? We have our victim. Our victim rents a virtual machine at a cloud provider, and they store sensitive data on that virtual machine. And our victim can be anybody, right? It doesn't really matter. And they store this sensitive data. It can also be anything, like your clients, your customer details, or your trade secrets, your private keys. Your private keys maybe that you want to use to sign your Deutschland tickets. Anything is possible to store on this VM. And we're going to see, as an attacker, what we're going to do with it. So our attacker, they have roots in another virtual machine running on the same physical hardware. And the goal of our attacker is to read this sensitive data covertly from the victim. So in other words, the attacker really prefers stealth without leaving any trace. To put this in a diagram, we have on the left our virtual machine, or our attacker virtual machine, and on the right we have our victim virtual machine. And each virtual machine will run on its own dedicated CPU cores, and they are managed by Linux KVM. And our attacker cannot communicate with the victim VM. They are like completely isolated to each other. So what is the attack that we're going to do? There's still like one thing that we can do here, and that is that we can communicate with the privileged process that manages everything, and that is the hypervisor. And we will look at Linux KVM specifically because it's used a lot in cloud environments. And the attack will roughly look as follows. The attacker will interact with the hypervisor in a seemingly normal way, But by doing that, the hypervisor will accidentally give the sensitive data of the victim to the attacker. And the cool part is the attacker does not need to involve the victim, so it does also not really matter what software is running on this victim's virtual machine. So how will the attacker do this? Instead of looking at the security of the software that runs on the system, we will take a look at the security of the hardware, and in particular the security of the CPUs that are executing all the software. And we're going to use CPU vulnerabilities for this. And they're very strange. They are bugs in the hardware itself. You cannot fully fix them by pushing a software update because, well, it is a hardware issue. It's baked into the hardware. And the only real proper way to fix such a vulnerability is to buy a new CPU. And as a disclosure, I do own one singular share of Intel stock. It's currently at minus 30, so help a guy out, I guess. So we're going to combine two known CPU vulnerabilities. And the first one is L1TF, or L1 terminal fault, and the second one is half Spectre. And when we're going to combine them, we will get something that is more powerful than each individual vulnerability. And in the end result, it gives our virtual machine access to arbitrary host physical memory. So what does this mean? Let's start with this with L1TF. This is also a very old vulnerability. It is 7 years ago. This was disclosed, August 2018. And with it, you can leak data out of the L1 data cache, ignoring any security boundaries. And with that, you can read cache from other processes that are running on the same core. Well, if you put it in a picture, it looks something like this. We have our physical core, and in that core, we have our logical core. We have our victim vCPU, some process doing some operations. It does some operations, it fetches some information from memory, and the CPU will keep this fetched information and store it in the L1 data cache. And now any subsequent operation on the same data will be much faster because it's stored in cache, so it doesn't have to go all the way to memory first before it can do its computations. And after our victim has done its computations, there's a context switch. Now another process is allowed to run, and in this case, our attacker vCPU is allowed to run. And the attacker can use this L1TF vulnerability to leak this data from the victim that was still in the cache and read it. And this is bad because an attacker can now read cache data from a victim. What do we do about it? Well, the real solution is to replace all Intel processors. And unfortunately, that is just infeasible, especially if you consider that between this time period, Intel sold almost $100 billion of their products, and that number is only considering even data center products. So all consumer chips that were also vulnerable are not included in this number. So there's a huge amount of processors that is still that were sold that were vulnerable to this. And replacing that all, that is wasteful, it's expensive, and perhaps even impossible, especially if you consider that the market for demand for these CPUs, for demand for compute, is much bigger than the supply. So you want to hold on to these chips. And that's why these chips are still out there. Like even to this day, these chips are being used by cloud providers. But for the sake of arguments, let's imagine we all replace these CPUs with AMD CPUs because, well, this is an Intel vulnerability, and AMD is cool and stuff, and Intel's dying. So if you do all that, everything will be good, right? Well, no, we have another vulnerability that was just disclosed this year. It is actually very similar. It also allows you to leak data out of the L1 data cache, ignoring security boundaries, like the same. It's not entirely the same. It doesn't work across SMT. We'll get to that a bit later. But this is still a hardware vulnerability that has a similar impact. So the real solution to this would be to replace all AMD processors. Yeah, and of course, you can already see that this doesn't work. So the industry very quickly realized that this is just waiting for the next vulnerability to pop up, and they have to replace all of them again. So this is not going to work. So when this was disclosed, the industry very quickly realized that buying new hardware, replacing millions of CPUs every time, that's just not possible or sustainable. So they need a different approach, and that is that they fixed L1TF in software with a software microcode update. And well, as you see, I put fixed between quotation marks because we'll see what happens later. So one of the solutions that they came up with is called L1 deflushing. It looks something like this. We still have a victim CPU doing some computations. Then by doing the computations, the data is brought into the data cache. Any subsequent operation, it will be faster, and then there's a context switch. And now, before control is handed over to the attacker, the data is flushed from the CPU. And now the attacker, well, it can still do L1TF, but there's no interesting data there anymore. So this sort of fixes it, right? For the TSA L1 vulnerability, the one on Intel, this does sort of address the issue. But for L1TF, there's still something that we should look at here. And that is something called SMT, or simultaneous multithreading, better known as hyperthreading, perhaps. And it's a very cool technique because it turns one physical core into two or perhaps more logical cores, and then you can share resources, right? Some core might be executing a program that does some arithmetic, some other core might be doing operations on memory, some other core might be evaluating a conditional branch. So all these cores might be doing different things, and now you can share resources on the same CPU. So that's like more efficient use, I guess. So considering this SMT thing, how does that work then with this L1 deflushing? Well, now it looks like this. We still have our victim CPU doing its operations, and after it's done, the cache is flushed. But simultaneously, we have our attacker that is running, that's executing. And before the flush is actually executed, the attacker can still do L1TF to leak this data, to read this data out of the cache. Okay, so SMT in this case is not great, so what can we do about it? Well, perhaps we can disable it. That is one way to do it. Unfortunately, that is, it's tricky. It's a huge performance penalty, and depending on your workload, it can be like 30% or higher even in some cases. So you don't want to do that, especially if you consider that this is like a very big scale that we're talking about. Like if you consider all the data centers in the world and you take 30% performance of it, that's like tens, if not hundreds, of additional data centers that you need to build. So it's insane how much that scales. It's very hard to imagine. So disabling SMT is not really feasible. So one thing you can do is something called core scheduling. And that is an additional constraint that we will put on the scheduler. And it ensures that the attacker and the victim are never co-scheduled on the same physical core. So if we put that into consideration, we have now core scheduling and L1 deflushing as a mitigation. We have our victim vCPU doing its operations, and only another victim vCPU is allowed to run simultaneously. The attacker is not allowed to run at the same time. And this is great because now we can ensure that all victim data is gone before the attacker actually takes its turn. So, okay, what now? With these mitigations, we have that the L1 data cache is flushed, so the data is gone from the victim, and we have the attacker that can no longer be co-scheduled with its victim. So, all is good. The attacker VM can no longer leak any data from another VM. But there's still a catch, and that is that the attacker virtual machine can still leak from the hypervisor. Okay, let's take a look. What does that look like? We still have a very similar picture, except now the victim is completely gone. We just have our attacker vCPU, and because of core scheduling, only another attacker vCPU is allowed to run on the same core. And at the top, we have our attacker vCPU. It's doing some interaction with the hypervisor, and the hypervisor will load some data into the cache, and simultaneously we have an attacker vCPU that uses this L1TF vulnerability to leak it at the same time. And there's this small window of opportunity that we have that the data is not yet flushed, it's still in the cache, and that we can read it. So, cool, okay, we can use this method to leak L1 data cache content that belongs to the hypervisor. And this is actually a known issue. So the Intel advisory to mitigate L1TF, it says, okay, avoid sharing logical processes on a core with different guest or host threads. So, okay, Intel says don't prevent, don't do this. And the Linux administrator guide also says that, well, host memory is still attackable in this scenario when you still have SMT enabled and you have, then the host memory is still available. So This is a known issue, and yet cloud providers still have SMT enabled. Because the manual, it's very clear, and the advisory is very clear. It says disable SMT if you run untrusted virtual machines on these particular vulnerable CPUs. Because if you don't, host memory is attackable with the default configuration. And yet somehow cloud providers keep SMT enabled on these vulnerable CPUs. But perhaps that is maybe a bit of a naive interpretation of the situation, because if you think about it, the performance cost of disabling SMT is just prohibitively expensive. At the scale of these enormous cloud providers, just a performance penalty of 5% means tens of additional data centers. So that costs billions, tens of billions, right? Business-wise, it doesn't make any sense. On top of that, if you consider that the fact that a lot of people consider this attack to be very theoretical, these are some anonymous quotes from the Linux kernel mailing list, where people are very much doubting whether this can be done in practice, right? So one person said, well, the practicality of such an attack is obviously an open question. Somebody else wonders whether the complexity of mitigating this is worth it. And somebody else even says, well, this is some virtualization-specific nonsense, I will ignore it. And okay, sure, I guess this attitude makes some sense if you work with the assumption that the hypervisor does not access any interesting data, right? The hypervisor is just processing a hypercall or an interrupt from a guest. It just works on the request from the guest, and it does not suddenly go and access sensitive memory, right? Well, maybe we can do something with it. Maybe we can trick the hypervisor into accessing some interesting data on behalf of us. Because if it would access some sensitive data, it would bring it in the L1 data cache, and then we can leak it again. And that is exactly where our second CPU vulnerability will come into play, half Spectre. Half Spectre is effectively this snippet of code, a bounce check. But crucially, it's with an index that we, as an attacker, control. And we have their bounce check, and it's followed by a load. And everybody that has used arrays in C knows that this is a very common pattern. It prevents out-of-bounds reads. Like this is great, but we're going to use it in a slightly different way. So let's walk through an example. Let's assume the size of the array is 10, so we pass our index. It's 5, okay, 5 is inbound, so this is all fine. The bounce check will succeed. Okay, now we'll go again, index is 9, 9 is less than 10, so this is inbound. This is all fine, and for performance reasons, the CPU will now predict the result of this branch the next time it comes here. So it will do something like, okay, just like the last two times, next time I will encounter this if condition, it will also succeed. And that's great, because now it can work ahead. It doesn't have to wait on the evaluation of this if condition. It can just compute the result already. And that works, because surely the next time this condition will also be in bounds. Well, no, okay, index is 1,000 here, so the prediction was wrong. But the CPU, it worked ahead for performance reasons. But something went wrong here. The CPU will roll anything back that affects the correctness of the code, so you won't really notice this. But it does not roll back the state of the cache. The state of the cache does not affect the correctness of your code, it only affects the speed of your code. Oh, well, a bit of a slowdown doesn't really matter in this case. But we can use this to our advantage. Now we have a branch misprediction, and the CPU actually executed this load, even though the prediction was false. And this is what we call a speculative out-of-bounds load. And the result is that the content of this X with index 1,000 is actually loaded into the L1 data cache. Okay, so that's half Spectre. Well, is there something like that in KVM maybe, in this hypervisor? Are there these bounce checks that are executed by the hypervisor? Well, probably yes, because it's a bounce check. Bounce checks are everywhere. Are there bounce checks that have indices that are controlled by us, by an attacker, by an attacker VM? And finally, is this index used in some interesting array that we can do something funny with? Well, it turns out yes, these gadgets do exist. This is one of them. So this is the variable dest ID. It's controlled by our virtual machine. And later on, we have our bounds check here. Dest ID is checked if it's within bounds. And finally, after that succeeds, we have our speculative loads here. This map-vismap array is loaded with Dest ID, which is the index of our choice. And when this element is indexed, it is brought into the L1 data cache. So what is this map-vismap array? What does it do? So this is an array that is located in the so-called direct map of the system. And it's a one-to-one mapping of your physical memory, like your actual sticks of DRAM, to the virtual memory of the kernel. And everything that is stored in RAM is accessible by the kernel via this direct mapping. And somewhere in here, we have this map-vismap array. And by triggering this half-spectre gadget, map-vismap will load something from the direct map from physical memory into cache. And the only thing is that we don't know yet what it's loading. So we are just loading something from physical memory into cache. So now we have two parts. We have L1TF and we have half-spectre. With half-spectre, we will load some physical memory into the L1 data cache. And with L1TF, we leak that out of the L1 data cache again. So if you combine them, you get our approach, which is L1TF reloaded. And again, it looks something like this. We have our attacker CPU. It interacts with the hypervisor. It triggers this half-spectre gadget, which will load something from physical memory into the cache. And simultaneously, we have our attacker using L1TF to read this data back from the cache. And this allows an attacker to read arbitrary host physical memory. So what's the content of this vismap array? It is an array with kernel pointers, exactly one kernel pointer per vCPU in our guest. And we know it's a kernel pointer because it starts with FFFF. And we can use this knowledge to our advantage. What we will do is, on one vCPU, we will continuously call this gadget with a Dest ID of 0, so we will load the very first entry of this vismap array into the cache. And on another vCPU, we will continuously try to do this L1TF thing, to try to all of physical memory. And at some point, it found something. And we know that this is correct because, well, we see again, this starts with FFFF, so these are two kernel pointers. And it's followed by zeros, which is sort of the pattern that we expect. So now we are fairly confident that with L1TF, we suddenly leak the content of this vismap array. So now we have established a relation between this Dest ID variable and host physical addresses. And if we plug in the address that we just found, the very first element of this map-vismap array, we can fill in any target address, any physical memory address in this formula, and then we know what Dest ID we have to give to this Spectre gadget, and then it can load arbitrary physical memory. So now we can pass arbitrary Dest IDs into this bounds check. And if we will call some misprediction in this bounds check, it will actually do the speculative loads with the Dest ID in our control, even though it might not be in bounds. Now, what do we leak then? Because our victim VM is somewhere in the direct map of the host at some Dest ID. We don't know this Dest ID. We could brute force it, but that will take a very, very long time, especially if you consider that these machines have hundreds of gigabytes of RAM, if not terabytes, somehow. And that's all accessible through this direct map. So brute forcing that just takes days or weeks or months, depending on how lucky you are, I guess. So how do we figure out what to leak? We should take a look at the content at these kernel pointers that are in the map-vismap array. It is actually a pointer to this KVM lab struct, and in that struct is another pointer, which points to a KVM vCPU struct, which contains another pointer, which contains another pointer, and et cetera, and eventually we will find this task struct. And this is a very helpful struct to us, because this is a struct that is part of a linked list, and it has all the processes of the host in it. So now it's a linked list. We can go there, and we can slowly start to loop through this linked list and read out the process names of the host. And you can see process names like QEMU or DOM, vCPU, Nanny, or others. These are like names of hypervisors, of virtual machine managers. And once we found something like that, we know, oh, this is an interesting process. And then we can continue from there and look at the root of its page tables. And from there on, we can start to translate the addresses of the virtual machine into addresses of our own virtual machines. So this is what we do. We call it 2D page table translation because it's a lot of pointer translation. It's a lot of page walks. We start with our attacker guest virtual address, and we go to our host physical address. Then we go to a victim guest physical address, and eventually we'll go to our victim process virtual address. So a lot of page walking. We do it in software, which is quite slow, so as a feature request to Intel, it would be great if the MMU could do this for us. Seems like a great feature. Might be something you want to look into. So throughout this process, we have a lot of pointers, and even a single byte that we misread will cause issues. So we do something called chase and check. We basically do a bunch of sanity checks, and if it doesn't work out exactly, or we don't get the exact results we expect, we go back and we try again, and this gives great results, actually. Well, that's a bunch of theory. Now let's show that in practice. We will have a root shell on a virtual machine under our control, and we will try to leak the private key from an Nginx instance running on the victim VM. And the cool part is we don't need to interact at all with the victim, so they won't see anything in their logs. This attack is like completely stealthy. So let's go there. So first we are trying to loop through all of the host memory. In this case, it has 825 gigs of memory. And we are trying to find this base address of this map vis array. And this takes actually a very long time, but once you have it, you can do this attack much faster. Once we found it, we will try to break kernel ASLR on the host, which is easier because we already know some of the bits. And once we've found that, it will take a while. We know where the direct map is, and now we can, you see this walking through these structs, and now we see all the processes on the host. So this is like a top on your hypervisor. And eventually we'll see a process that looks interesting, Nanny in this case, which is the name of the thing in Google. We'll look through all the open file names here, all the open files, all the file descriptors. And this is still sped up, by the way. So in reality, it takes some time. But okay, now we found the KVM struct that we are looking for. Once we know that, we can translate our own pointers to the pointers of the guest. And you see a lot of pointers being read and dereferenced. Now we're going to break kernel ASLR on the other guest, so on the victim. We now know where the kernel of the guest is located. And now we're going to basically do a top on the other guest. We're going to see again this task struct, this linked list. And we're going to try to find Nginx. So we see systemd, PID1, SSH, D, okay, Polkit. And there's Nginx. Now we're going to try to figure out a way to translate our addresses to addresses in the Nginx process on the ghost, on the victim. And now we're trying to find the private key on the heap of Nginx. And we just found it. Now we're going to try to leak it. We do use one thing to our advantage, and that is that well, this private key, it consists of prime numbers, and this process is a bit, it's not 100% accurate, but we can do a primality test to see if it's actually a prime. well, this is not. This is a composite number, so we know we leaked some wrong bytes, but we can try again. And now we found 1 prime. And there it is, we found both primes, and we have the private key of our victim. In reality, this took 6 hours, so I'm not doing a live demo. There are some parts that you just need to do once, and then you know a bunch of magic values, and the attack is much faster after that. We sent this to Google, and they very quickly asked, they acknowledged our report, and they asked for a proof of concept. We gave it to them with a bunch of meetings, and then on May 29th, they gave us a $151,000 bug bounty, which is actually... And it's actually the highest bug bounty they've ever given out, so that is very cool. It will also be the highest bug bounty for a while, because they changed their bug bounty program. But in general, like a 10 out of 10 response from their security team. They were like very responsive. And on August 11th at Y, we had the public disclosure there. We also did the same on AWS. There we had very different results, and that was because we were not able to leak much more than just metadata. We were unable to leak from other guests, and that is because AWS uses its own custom KVM-based hypervisor. It's called AWS Nitro, and there's some additional mitigations specifically to take this into consideration. And one of them is exclusive page frame ownership, which we will talk about in a bit. We were also in contact with some other providers with mixed responses. One of them said this: please understand that we can make no comments on whether we are affected, as this is highly sensitive information. Well, I can only interpret it one way. I have redacted their name. I don't want to get sued by this database company that inexplicably employs more lawyers than their engineers. So, and that's not all, because at some point, August 14th rolls around, which is 3 days after the public disclosure. Like, everything we did was public at this point. This same redacted company sent us a new message. We appreciate it if you can extend the embargo period on this report. Well, oh boy. So now a big question is, like, has this been abused, used? Well, who knows, right? It's a very strange vulnerability. This thing has been known theoretically for at least 7 years. And nobody really seemed to have bothered to look at this, at least not until a board master student came along, I guess. And it's very tricky to answer this question, because there's no logging. Nobody's logging their hypercalls. There's no anomaly detection here. And, of course, there are no traces, right? It's completely invisible. It's all based on speculative execution, so who knows? So how do we mitigate something like this? How do we design even better hypervisors? Right now, there are 2 proposed mitigations in the Linux mailing list. Performance of both is not great. One of them is exclusive page frame ownership. That's the one that Amazon has used in their hypervisor. The other one is address space isolation, which Google is rolling out in their fleet. So exclusive page frame ownership, it looks something like this. We have our host virtual memory, which has all of the direct map. We have our guest physical memory, and we basically do an XOR, and we get that out of the direct map. That's the very basic summary of it. The other mitigation is address space isolation, and it looks something like this. This is without it, this is the current situation. We have our guests, and we are now in the hypervisor, and all of the memory of all the other guests is in the host memory. And with address space isolation, we're now running in guest A, and when we go to the hypervisor, before we go to guest B, we will first switch around the address space, and then we go to guest B. And if we go back, we do the same again, and then we go back. So there are 2 mitigations that are currently being upstreamed. So what can you do in the meantime? Well, this specific gadget has been removed from all Linux releases since September. So update your host kernels. These two mitigations, they are being used in production at AWS and Google. And they are being upstreamed in the kernel, but it's a tricky process because, well, performance is tricky. So what you can do is, if your CPU is vulnerable to this, disable SMT. But of course, you will take a performance penalty for that. Also, ask your cloud provider, how do they keep their host kernels up to date? Because updating your host, well, you need to live migrate your virtual machines to another machine. It's not an easy process, so try to ask, like, how do they do that? Do they also keep their microgrid up to date? That's also not a given. Do they use core scheduling or disable SMT? These are like things that your cloud provider should probably have an answer for if they are trying to mitigate these type of issues. Of course, it all assumes like this falls within your threat model. If it does, then you can also consider just getting a dedicated machine or self-host. It's a lot of fun. And then you don't have to worry about any of these attacks really anymore because you control the entire machine. And before we conclude, I would also like to give credit to a bunch of people. This project started out as my master thesis at the Vrije Universiteit Amsterdam. And it's sort of spiraled out of control from there. First, I would like to thank Mate. He helped me throughout the entire process, iterating on my initial proof of concept and for the immense amount of work that it took to get it working fast and reliably on the cloud. I would also like to thank Dave for supervising as well, and finally Marius, Herbert, and Eric for supervising me and giving their guidance and feedback and expertise throughout the project as well. So if you want some nighttime reading, we have published our code on GitHub as well, and there you can also find a link to our upcoming SMP paper and some links to more detailed and technical blogs from both Google and Amazon that they wrote about our research. So thank you.
Please give it up for Thijs. A very warm applause, please. Thank you for this talk about the ghosts, the vulnerability ghosts that still haunt us today. So we have time for very few questions. If you have some questions, please step forward to the microphones. And please remember, keep it a question and not a comment. Please start with microphone 2.
Yeah, great to see a Dutch guy on the stage. Very cool research. I have, of course, not looked at the GitHub yet. I kind of missed, did you leak the CR3 to do the editor translation, or?
Yes.
Okay, thanks.
Microphone 1, please.
Yeah, so you said that for this to work, you need to have like the attacker and the hypervisor like sharing one physical core, which immediately got me thinking, like, couldn't you fix this by just like not allowing anything else to run on the same core, just have the core reserved for the hypervisor? I assume if that worked, you would have mentioned it, so why doesn't it?
So people have thought about this. This is research that people have done, like, is this feasible? It is very tricky to do this, especially if you want performance, because now that means that every time you do a hypercall or every time you exit to the hypervisor, you have to go across a core. And like, how many cores do you reserve for the hypervisor? Like, it's very tricky. And there is a proposal in an academic paper that sort of tries to do this, but I think it requires some modifications to the hardware as well. So it is possible, but it requires a lot of overhaul, because now you are sort of assuming that your privileged process is on a different core, as if it's similar to like if your kernel is on a different core than your user space programs. It becomes very tricky to reason about how that exactly works. It is possible, but it requires like a lot of rewrites and thinking to get that working correctly and fast, especially. So that's not something that is really feasible at the moment, I think.
Thank you. Microphone 4, please.
Hey, I was wondering what side channel you're using to retrieve the data after rollback, because I thought cache-based side channels would be way too slow and also error-prone, or is it just fine?
So we use it. We measure the amount of time it takes to retrieve an entry from the cache.
Yeah.
And this is error prone, that is true, but because we use this chase and check method, if we encounter errors, we will notice it because we sort of have these sanity checks. Oh, we do expect this type of data, and we don't get it, so we can retry these specific parts, and then you sort of eliminate most of the effect of the error.
And still find that you get it in 6 hours, because I thought it would take much longer with...
Initially, it took much longer, but we optimized it away.
Okay.
Okay, now microphone number 2, please.
Thank you. Short question. When you think about environments that use containers and not VMs, for example, Kubernetes, can you explain how these environments are affected by those vulnerabilities?
So it's about like if it is in containers and Kubernetes, for example, whether it's in that case, how is that vulnerable? In this specific case, no, because to use L1TF, you need to do some strange things which with modifying your own page tables. And that is not something you can do in Kubernetes because you don't have, well, hopefully you don't have like root access and you can modify your host. Hopefully you cannot do that from your Kubernetes guest, otherwise you have a problem. So in that scenario, it doesn't work. This research is specifically about like if you are like in a virtual machine, because then you also have the ability to change your own page tables, and you need that to trigger this L1TF vulnerability.
Okay, thank you.
Question from microphone 1, please.
Yeah, thank you. Are there any known mitigations foreseen for future CPU architecture, like that you kind of try to get rid of this side effect of the branch prediction? You know, so that you kind of remove it quickly enough without losing performance. I mean, we do not want to have this around in 10 years. So is there anything already, to your knowledge, around that will mitigate this in future architectures?
Well, you mentioned like without losing performance, so that does a lot of heavy lifting, because the branch predictor is very important for performance in modern CPUs. If I remember correctly, about on average, on your like, if you look at the instructions on your, if you look at the instructions on your that are happening on like generic Linux programs, I think 1 in 6 instructions is a branch, is a comparison. So it is a lot of your instructions. So you want to optimize that in some way, and the branch predictor is very crucial to do that. Because if you don't do that, the CPU likes it if all your instructions come like right next after each other and after each other. And if you throw branches in there, you don't exactly know what your next instruction will be, and you break this nice property that CPUs would like, that all your instructions come after each other. So without a branch predictor, it is very tricky. I don't know if any like CPU that wants to achieve performance even thinks about this.
Very last short question from microphone 6, please.
Yeah, so I have a follow-up question for the Kubernetes question. What if the same hypervisor runs the attacker VM and the victim VM that runs Kubernetes cluster?
Oh yeah, that would work. Like the thing about this attack is that it doesn't matter what software the victim is running, because we're not really targeting the victim, we're targeting the process that manages everything. So if you have a VM where an attacker is allowed to do this, and another VM that runs any workload at all, doesn't matter, you can extract secrets or data or anything, yes.
So you don't want to run Kubernetes and normal VMs on the same hypervisor, right?
Well, sure, yeah. I guess not. If you want to prevent against this specific attack, then don't do that.
Yeah. Okay, thanks.
Okay, Thijs, will you be available for more questions after the talk? Where can we find you?
I had my my Mastodon and my
Maybe dancing at a dance floor somewhere.
I might be there, but I might also be at the Tech Assembly. So if you show up there, then I might also be there.
Okay.
Otherwise, just talk to me, I guess.
Meet him later. Please, a warm applause for Thijs.